In this lesson, students will apply similarity concepts to polygons and circles. So first we're going to define similar polygons. Just like triangles, similar polygons can have the same shape, or they have the same shape, but can be different sizes. So again, in similar polygons, corresponding angles are congruent because that's how they maintain their shape. And corresponding sides are in proportion. So let's say I have a polygon that's a multi-sided object. So I can just draw this quadrilateral here. And we'll call that ABCD. And again, when you're labeling, you go around. Oh, I can't even label right while I talk. A, B, C, D. You can't go back and forth. You have to go around. And let's say I'm going to do as best as I can to draw a similar shape. Let's say these two are similar. So we have E, F, G, and H. So for polygons, we just label them by all the letters around. A, B, C, D is similar to E, F, G, H. That means if I'm marking up the angles, angle A and angle E are congruent, B and F, C and G. I'm going to do 4 of them here, D and H. But again, you can't say that about the sides. For the sides, you set up proportions. So AB over EF, because those are corresponding sides, is equal to BC over FG, which is equal to CD over GH, which is equal to DA over HE. Okay? Now with that, any pair of corresponding dimensions will also be in proportion. Let me see if I can scoot that up a little bit, and then we can write that. Okay, so I'll say it again. Any pair of corresponding dimensions will be in proportion. So, for example, if I just draw a segment connecting AB to AD, and I draw the same segment, in the same general location, those two would also be in proportion. So if this is XY and this is WZ, I could also say that AB over EF is equal to XY over WZ. That's another proportion that's the same ratio as all the other corresponding sides. So next we're going to talk a little bit about circles. And circles can be completely defined by just one dimension, the radius. That's the only dimension you need to make a circle. So, because of that, anytime I have two circles, I can always create a scale factor between them because there's only one dimension in a circle. Therefore, every single circle is similar to every other circle because you can always write a scale factor between them. So let's look at an example of this. I have circle A with a radius of 2, circle B with a radius of 3. And in this problem, I want to determine the scale factor that maps B to A. So I start at B, I end up at A. How do I scale this down so I end up at A? So all we're looking for is the scale factor. It's just the ratio. And remember, it's end over beginning, so it's going to be, I'm ending at A, it's going to be A over B, or the radius of A over the radius of B. So in this case, it's going to be 2 over 3. That would be the scale factor to move circle B to circle A. So here's a verbal question. The radius of circle A is 2.7. The radius of circle A prime is 11.3. Again, find the scale factor that takes circle A to circle A prime. end over beginning. So all you have to do, don't make it complicated, the scale factor is going to be 11.3 over 2.7. And I don't know if that simplifies down. You'd have to check it with your calculator. And it really doesn't simplify. If you put it in the calculator, you get the fraction 113 over 27, which is the same as 11.3 over 2.7. So you really can't simplify that one. So we can talk about squares in the same way. Squares are defined by a single dimension, which is their side length. So that's all I need to know. I need one dimension and to know that it's a square. And all squares are going to be similar to all other squares. And the reason being is because all four angles are 90 degrees. And if you have one side length, all four side lengths are going to be the same. So any square is going to be similar to any other square because corresponding angles will be equal. They are still 90 degrees. If that's side 1, side 2, I have a single dimension, and the scale factor can be side 2 over side 1. So that would work. So finally, we're going to do a few examples that you'll see in the textbook. I have two rectangles here. They are similar to each other. I want to find the length of their diagonals. So first of all, to find the diagonal length, you need to use the Pythagorean theorem. I've talked about the Pythagorean theorem a little bit. A squared plus b squared is equal to c squared, just in case it's been a few years since you've seen that. So the hypotenuse, the longest side, which is the diagonal of the rectangle, is always on the side by itself. And again, it's very similar to the distance formula. If I say 15 squared plus 20 squared is equal to c squared, then c is going to be the square root of this side, and that's the square root of 625. So c is going to be 25. Now you don't have to do the same thing over here because, like I said before, corresponding dimensions are going to be in proportion if the two figures are similar. So if I'm trying to find x over 25 is equal to 12 over 15. That's one way to set it up. You do corresponding sides, and the 12 goes with the 15. So you cross multiply, you get 15x is equal to 300, and so x is going to be equal to 20. So the diagonal of the second rectangle, the smaller one, is 20. So here's another kind of word problem. This is another one that's from your book. An elementary school building is building a gym, and they want to have the same relative scale as the high school gym. But the high school gym is bigger because in the elementary you only have a width of 42 to work with. And we want to find the appropriate length that will keep this in the same scale as the high school gym. So again, corresponding, you can do corresponding sides and set up a proportion. X over 84 is equal to 42 over 50, and then you go from there. We cross multiply, we get 50x is equal to 3,528. When I divide, you get 70.56. Depending on how they want to round, you could say roughly 71. If the bigger length is 84 feet, then this would be about 71 feet to keep it to scale. And then finally, we have the type of problem that pretty much forces you to use a scale factor because you're not given enough dimensions. Two rectangles are similar. The smaller rectangle is 7 by 10. What are the dimensions of the larger rectangle if the scale factor is 1.5? So you can draw your rectangle. This is 7 by 10, and I don't know what the bigger one is. All I know is that the scale factor is 1.5, okay? So R is 1.5. Let's say X and Y. Well, 1.5 is what you put in for the other ratio. So if I'm trying to find X, I could say X over 7 is 1.5. That's one way to do it. If you really like proportions, that's one way to do it. In the end, you're multiplying 7 by 1.5, which is what a scale factor does. It scales it up, and that's going to be 10.5. So you can set it up with a proportion, or you can just know that, like for the next dimension, I take 10, I multiply it by the scale factor, 1.5, and you're going to get 15. So those are the two different ways you can do it. And that is basically the types of examples you should see in your textbook or your bookwork today, using scale factors and proportions to find the missing sides of similar shapes.